So this will be the first lecture over chapter 15, so lecture over dienes. So in this lecture we'll look at how to name them, look at their basic general properties, and look at this different stabilities of the different types of dienes. With regards to naming them, it's pretty similar to how to name an alkene. So if we were to name this diene, so 5 carbons would be pentane. And so normally, we would, if it's an alkene, we would change the A to E. In this case, if it's a diene, then what we're going to do is we're going to keep the A to make it easier to say, to pronounce, and we're simply going to add diene at the end of the word, so it's going to be a penta. So we're going to keep the A, but then we're just going to say diene. But then we need to specify where the 2 alkenes are at. So we need a number for each where the double bond starts at. So it starts at 1. The first one starts at carbon 1, and the next one starts at carbon number 4. So, and we put commas between numbers and dashes between letters and numbers, so that would be penta 1,4 diene. So in this case, with the cyclohexane would be the parent. And then we're just going to stick diene here. So, and the double bond starts at carbon number 1 and at carbon number 3. So that would be cyclohexa 1,3 diene. And so similarly for trienes, of course we would start numbering from the left because then the first double bond would start at carbon number 1. If we started numbering from the right, then the first double bond will start with carbon number 2, and we want to keep the numbering scheme as low as possible, so we number from the left. So 7 carbons would be heptane, and then we're just going to stick triene here instead and indicate where each double bond starts at. So that would be hepta 1, 3, 5 triene. And then this one has a little bit more detail that you have to involve. So anytime you have double bonds, of course, you always have to look out for stereochemistry, cis and trans. So there's no stereochemistry here, but there are stereochemistry at the other 2 double bonds. And the first one that we did, there's no stereochemistry there or there, right? There's no cis and trans because carbon number 1 has 2 hydrogens and carbon 5 has 2 hydrogens. So they don't have cis and trans possibilities, but in the triene, the double bond at 3 and double bond at 5 does have cis and trans possibilities. So you have to know where the hydrogens are at. So the hydrogens are there, right? So that you have 120-degree bond angles. And there would be a hydrogen here and a hydrogen there. And so now if we assign priorities, so this is number 1, that's 2. This is 1, that's 2. So those are ones are opposite. So that one's trans. And if we did the same thing here, split that double bond, this is 1, that's 2. This is 1, that's 2. So those ones are opposite, so they're both trans. So this would be 3E or 3 trans, 5E or 5 trans, hepta 1, 3, 5 triene. Okay, so in terms of their stability, so there's different types of double bonds. So this one, where the double bonds are on adjacent carbons. So this would be 1, 2, well, penta diene. So sometimes you see the numbers at the start of the parent. That's the old way of doing it. The more conventional way of doing this is to put the numbers right before the letters in the functional group that tells you what it is. So that's a 1, 2 diene, and this type of diene is what's called accumulated diene. And in this case, 2, 3, 4, 5, 6, So this type of diene is what's called an isolated. An isolated diene, because there is an sp3 hybridized, at least one, there could be more, but if there's at least one sp3 hybridized carbon in between them, then the dienes are said to be isolated from each other. And in this case, there's not. There's no sp3 hybridized carbon in between them, so this type of double bond is what's called a conjugated. And so the significance of double bonds, so if you remember, if you have an alkene, then each of these carbons has a p orbital on them. So if we were to sketch what those p orbitals look like, all right, so each carbon has a p orbital. And each of those p orbitals has one electron in it. So we're letting these two p orbitals, which are on adjacent carbons, overlap to make a pi bond. And we're letting those two p orbitals, which are on adjacent carbons, overlap to make a pi bond. But the significance here is that these two p orbitals are also on adjacent carbons, so why can't they overlap? And the answer is, well, they can overlap, and they do overlap. So all of the p orbitals overlap with each other, and so that means the electrons are free to move from any p orbital to another p orbital. So we can, for example, take that electron and move it here, and we can take that electron and move it here, and we can take that electron and move it into that p orbital. So basically what that means is we can draw resonance structures. If you remember what resonance is, it's the delocalization or the movement of electrons through pi systems. And so since all of the p orbitals are on adjacent carbons, then they can move from one p orbital to another p orbital. So we can have two electrons here, one here and one here, and none here. So now this carbon's electron deficient, so it's positive. This carbon's electron rich, so it's negative, and then we can let these two p orbitals overlap to make the double bond there. Or using this picture, basically what we did is we moved that double bond there, and we moved these two electrons onto that carbon, or into that carbon's p orbital, to make a lone pair of electrons. So now that carbon's electron deficient. Now the double bond is between carbons 3 and 4, and now that carbon has a lone pair, and so it's electron rich, it's got a negative charge. So the point is, anytime you have conjugated double bonds, then that means the electrons in the p orbitals can move between the p orbitals, so you have resonance structures. But in this case, if it's an isolated double bond, so here we have carbon with two hydrogens. So that carbon in the middle has two hydrogens on it, so it does not have a p orbital. So if we sketch the pi system here, right, then those two p orbitals are on adjacent carbons, so they overlap, so there's a pi bond there. And then these two p orbitals are on adjacent carbons, so they overlap to make a pi bond. But because there's an sp3 hybridized carbon in the middle, there is no p orbital there, so the electrons in the pi system, let's call that pi system 1 and pi system 2, are isolated from each other, and those electrons cannot move from pi 1 system to pi 2 system, and vice versa. Okay, so of course for this first one, when the resonance structure we drew, we could have gone the opposite way. We could have moved the electrons this way just as well. So we could have put the negative there, and the double bond there, and the positive there. So there's two different resonance structures that you could have drew for that diene. So that affects their stability. So if we look at the relative stabilities of alkenes, and so one way that you can look at stabilities is for alkenes, if you do a hydrogenation. So if you remember, if you take an alkene with H2 and palladium or platinum or some metal catalyst, that will add hydrogen and hydrogen across the double bond, and so now you have an alkane. So if you did that for the 1-pentene or the 2-pentene, if you added hydrogen and hydrogen across a double bond, in both cases you make pentane. So you make a common product, you make pentane. So then if we look at how much energy comes out of this reaction, then that will tell you, or the heat of the reaction, the enthalpy of the reaction. So if we measure how much heat is evolved in this reaction, so if we took the same amount of each one, since they have the same molecular formula, they have the same molar mass. So if we look at how much heat comes off per gram or whatever per mole, then we can figure out the stabilities of the different alkenes. So if you did this for the 1-pentene, then the heat that comes out of this is negative 126 kilojoules per mole. So it's exothermic. It gives off, for every mole of 1-pentene, it gives off 126 kilojoules of energy. And if you did this for the 2-pentene instead, it's only a negative 114. So that would be, this would be delta H for 1-pentene. And 2-pentene gives off less heat. They both go to the same product. So if it gives off less heat, then it must have been more stable to begin with. So of course you know it's more stable. Why is it more stable? Because this is a disubstituted alkene. If you remember the stabilities of alkenes from organic 1, and this is a monosubstituted. And of course disubstituted alkenes are more stable than monosubstituted alkenes. In this case by 12 kilojoules per mole. Okay, so if we did the same thing for the diene, so if we took the isolated diene, so this is C5H, 1, 2, 3, 4, 5, 6, 7, wait a minute, 1, 2, 3, 4, 5, 6, 7, 8. So C5H8, and this is the conjugated version of C5H8. And if you do hydrogenation on both of the double bonds, then they both go to pentane. So just looking at how much heat comes off will tell you which one is more stable. So the isolated double bond gives off negative 252 kilojoules per mole. And if you notice, that is twice this. If you had one double bond and had H2 and palladium, it gives off 126. If you added 2, it gives off 252. Which is not surprising because the two double bonds look identical, right? It's just 2 1-pentenes, so to speak. So then what you might expect for the conjugated double bond, so if we took the 126 and we took the 114, since we have a monosubstituted and a disubstituted, right? We have a monosubstituted and a disubstituted double bond, and if you added those two together, that would be 240 kilojoules per mole, which might be what you expect. But what you actually get is negative 225. So that's a difference of 15 kilojoules per mole. So the conjugated double bond is 15 kilojoules per mole more stable than it should be, based on simply the fact that you're hydrogenating a mono and a disubstituted double bond. So where does that extra stability come from? It comes from the fact that these two double bonds are conjugated, so you have resonance delocalization of the electrons, and that stabilizes the double bonds. Whereas if they're isolated, the two double bonds are not in resonance with each other, and so those double bonds are less stable. Okay, and what if it's accumulated double bonds? So the double bonds are on adjacent carbons. So if you did the hydrogenation here, negative 292 kilojoules per mole is what you get. And in this case, again, you have a monosubstituted double bond, and you have a disubstituted double bond. So you might expect to get the 240 but the actual is negative 292, and so in this case it's 52 kilojoules per mole less stable. So it's 52 kilojoules per mole less stable than it should be, just from the fact that you have a mono and a disubstituted double bond. So basically the stabilities of dienes is conjugated or more stable than isolated, which are more stable than cumulated. Okay, and then there's another type of double bonds, and this is what's known as the S trans isomer, and this is what's known as the S cis isomer. So what does that come from? The S stands for single bond. So here there's a single bond, right, between the two double bonds. So these are both conjugated double bonds. But one of them is more stable than the other, and the one that is more stable is the S cis isomer, or the S trans, sorry. So it's more stable than the S cis isomer by about 12 kilojoules per mole. And what's the reason behind that? Is because if it's the S cis isomer, then these hydrogens are close in space, and that destabilizes them because they're trying to occupy similar space, or same space, so there's a steric interaction there. So the S trans isomer is more stable than the S cis isomer. But the diene does want to be flat, because if it's flat, then you have conjugation, right? So it can be flat S cis or it can be flat S trans. In both cases, you still have conjugation. So the double bonds, if these are the two double bonds, they want to be flat, either like that or like that, but they don't want to be perpendicular to each other. So you don't want to rotate around this double bond 90 degrees. Because if you did that, right, then the p orbitals are not in the same plane and they're not conjugated then. So that breaks the conjugation. So it wants to be flat. Right, those are the double bonds, either like that or like that. That way they're still conjugated, but they don't want to be like that, because then the p orbitals are perpendicular to each other and there's no longer conjugation. Okay, so what you might have to do in this chapter is simply I give you some dienes and ask you which is more stable. So if you had that diene or that diene, which is more stable, or classify them. So this is isolated and this is conjugated, so this would be more stable, right? Or maybe I would give you one in an S cis versus an S trans conformation and ask you which is more stable. So then you simply have to know that conjugated is more stable than isolated, which is more stable than cumulated, and S trans is more stable than S cis for steric reasons.